Hello there, my name is Richard Cooper. I'm a vet and nutritionist working in the southwest of England. This webinar is designed to report on a case study that was funded by Farming Connect, looking at the impact of urea or potential impact of urea on fertility in a farm in Cardiganshire. So to give just a bit of background to the project, this project sort of came out of a conversation that took place between a Farming Connect member and a farmer over in coastal Cardiganshire. We'll call it Farm P for the sake of argument. 270k units of sort of productive cows, doing very high compositions around, well, just under 5% butterfat, 3.2% crude protein. So the herd that's sometimes grazing when there's sufficient grass available, but certainly in the year this took place and the year before, cows weren't turned out to grass at all. The farmer himself made an observation that they felt that when bulk milk ureas, as reported on their milk quality reports, rose, there appeared to be a sort of a drop off in the chance of cows actually holding, so their conception rate, if you like, dropped over during that period. So the project started around the beginning of summer 2019. The first thing we did is obviously have a look at the bulk milk urea just to see what degree of variation there was. And certainly around the time of the project starting, we're going through a period of having very high bulk milk ureas. So I would call anything around 0.035% bulk milk as being high enough to sort of have concerns over. Like most units, of course, we see variations with this urea across the seasons. In many situations, of course, a lot of these fluctuations are caused by grazing, and particularly the amount of sort of soluble or very certainly very degradable forms of nitrogen that appear at different stages in the grass growth cycle across the seasons. But in this case, actually, this was a herd, as I said, that did not turn out, and actually this latest change appeared to be in response to the feeding of some third cut silage, which wasn't particularly special. I think it's probably worth just reminding ourselves about protein in feeding in dairy cattle. So when we talk about the sort of protein content of feeds for cattle, we tend to talk about this term crude protein. Now, crude protein is a little bit deceptive in the sense that it is, if you like, an indication of the amount of nitrogen within a feed, not necessarily the amount of protein. Now, of course, under most circumstances, the main source of nitrogen within a feed is protein, but it doesn't tell you anything about that protein at all. It doesn't tell you about its quality. It doesn't tell you quite what it's going to do in the rumen. It just is a number, and in fact, it is literally the nitrogen content of the feed multiplied by 6.25. Why 6.25? Well, that is the average weight of an amino acid, one of the building blocks of protein. So it is a very, very rough approximation of protein content. So if you wanted to increase the crude protein content from grass silage, you could go outside and take a leak and relieve your bladder on it, and you would actually increase the crude protein content of that grass silage significantly. But you wouldn't have obviously added any quality protein or any protein as you and I would know it. So again, it can be this true protein when we look at the figure. Again, it doesn't tell us a lot about the solubility and degradability, or it can be genuine non-protein nitrogen. So we will find obviously ammonia in some feeds, particularly conserved silages. It could be urea. So if you're adding feed grain urea, obviously that has a significant level of nitrogen in. In fact, if you talk about it in crude terms, protein terms, I think it's around sort of 585 to sort of 600% crude protein, which of course sounds like complete nonsense, and is. So in order to understand urea and where it comes from, we need to go back to how we feed protein to cows and what cows do with protein. So protein has two basic fates within the rumen. So it can either effectively move through that rumen and through the abomasum and into the intestines without being in any way altered or degraded by the bugs, We tend to call that rumen undegradable protein, rather obviously. And again, that gets digested in the intestine the same way that monogastrics like ourselves and pigs would tend to digest protein. However, the vast majority of protein that we feed our cows gets degraded by the rumen bugs. What do I mean by degraded? They effectively dismantle it, and that gives them a source of energy. So they dismantle it all the way to a very base level, and the base level of nitrogen is ammonia, basically. If those bugs have an energy source, then they can effectively capture that ammonia and build it back up into protein. And the sort of protein they build it up into is obviously microbial protein. It's effectively new bugs. That microbial protein, some of the microbes will be washed out of the rumen into the abomasum, and they will be digested in the intestine. So most of the protein that a cow actually digests and uses is actually her own rumen bugs. A small proportion, or sometimes a significant proportion, of that degraded protein, ammonia, doesn't get captured as microbial protein. Ammonia is a very small molecule. It travels wherever it wants. It will go and drift through various things. So ammonia, that uncaptured ammonia, will drift through the rumen wall and it will enter the blood system of the cow. Ammonia is incredibly toxic, and so the cow quite advisably gets that ammonia and runs it through the liver, and the liver tends to make that ammonia safe by converting it into a slightly less toxic substance, urea. So to recap, effectively, when we give protein to cows, they break it down to the most base molecule, ammonia. If they have a source of energy, they can then take that ammonia and turn it into microbial protein that the cow herself can then digest. But if they don't have enough energy available at the time, or if they're completely overwhelmed, so effectively there's too much protein hitting the rumen in one go, they physically can't process it all fast enough and multiply quick enough to capture it as microbial protein. So in those circumstances, you get a sort of a sudden buildup of ammonia, it washes into the bloodstream, and cows then convert it into urea and pee it out, or try to recycle some of it in the saliva. So when we're feeding cows, we want to make sure there's a constant trickle of protein and energy to the rumen, so the bugs can do what they do and make some microbial protein. So you'll hear a lot of things in the past about balancing the proportion of degradable protein and fermentable energy in the ration to make sure that we have something that the bugs can work with. So what we know is, again, urea is a small molecule, it gets everywhere, and actually if we look at and we try and correlate milk urea with that's in the blood, they are very closely related. It's not a perfect relationship, but certainly looking at milk urea does give us an indication of what might be going on in the cow's blood. This obviously isn't a perfect thing, as you can see from this scatter plot that was done by Broderick and Clayton. If you look at your blood urea and your milk urea, there's a fair bit of scatter as well as a decent correlation there. There's usually a sort of a lag of about an hour between the two. So if you have high spike in urea in the blood, an hour later you'll start to see that in the milk. There are other influences of milk urea that we have to consider, which accounts for some of the scatter and the sort of mess on that graph. And that's effectively things like water intake. So cows are taking more water in and they're peeing more urine out. They tend to obviously wash that urea out of the system a bit quicker. We know that feed impact has a bearing. So in general, if you go and look at cows, the urea is highest about 6 hours after the main feed, and it's at its lowest immediately prior to feeding. The feeding method, of course, is quite important. So if you've got animals fed a component ration, so in other words, parlour cake, where they go in and take a big meal and all in one go, you would tend to have higher urea than TMR, because of course the bugs get slightly overwhelmed by the amount of protein suddenly landing there in one go. And we know there are other factors as well, such as parity, the number of calves a cow has had, season, breed, and so forth. So we know that obviously urea is produced and it can appear in cow's blood and milk. Why should we really care about it? Well, the first thing is that urea actually has a very high energy cost to produce. So in order to take that ammonia and to make it safe, the liver has to burn a lot of energy. That energy that it's using to produce that ammonia is of course not going to other useful purposes. So for example, lactose production, so effectively you can lose milk in very high urea rations simply because the energy that would have gone to producing lactose and subsequently milk volume is actually going to dealing with all of that nasty ammonia. And this of course is going to be particularly pertinent for early lactation animals who are already likely in sort of negative energy balance. And to then add another energy cost on top is going to potentially put them into severe negative energy balance and might result in fat mobilization and ketosis, for example. The other sort of stating the obvious thing is, of course, protein feeding is generally quite expensive. It's not very efficient to feed nitrogen or protein to cows that is not used for something useful and is peed straight out the back end. So if we're looking for economic efficiency in feeding our cows, we don't want to be getting a huge amount of urea produced. Stemming on from that, of course, there is an environmental impact to this. So we know that nitrogen can be excreted in the dung, in urine, and this obviously risks runoff, pollution incidents, or volatile losses. And then, of course, the last one is an interesting one that we're going to focus on today, which is, of course, that urea may negatively influence fertility and a chance of an animal conceiving. So this idea that urea might influence fertility is quite an old one. The idea has been out there for a very long time. It's been very controversial up until, I'd say, fairly recently. The reason for that is that when people have done these sort of studies looking at urea and whether it has an effect, some found a relationship and many others didn't. So it was fiercely debated amongst academics. So in general, let's say that the controversy is dropping off. In fairly recent times, we've had some good research that has looked in more detail at how urea might influence fertility, and there's been obviously some experimental studies to look at and examine some of these ideas. So we do know that certainly there's a very strong relationship between negative energy balance and fertility. So animals in severe negative energy balance will tend to have things like lower levels of IGF-1, sort of growth, if you like, a growth planning hormone. And unsurprisingly, if you've got animals in profound negative energy balance, Mother Nature tends to say, well, if you can't look after yourself, you're not going to be able to look after a calf. So I'll try and decrease the chance of you getting pregnant. There are more direct influences as well from metabolic disease. So if we think about NEFAs, which are the fat in the blood caused by cows mobilizing a lot of their body reserves very quickly, we know that those have a negative impact on fertility in a number of ways. And equally, subclinical ketosis, so high ketones in the blood, we also know has an impact as well. So certainly that's probably one of the major causes of urea and negative fertility. But people have done some work actually looking at direct toxic effects on particularly eggs and early embryos. So we know that high urea can alter the egg's development. If you like, the egg has to be primed before it's sort of released, and the presence of urea can actually alter that. And there has been work to say that the urea itself can change the uterine environment. So if you imagine the uterus has a form of fluid in there which is very sort of nutritious and is there to help the embryo grow, urea has been shown to change the levels of different ions in that fluid, and obviously it can actually alter the pH within that uterine environment, which can then influence the early embryo and how it grows and develops. And also we do know that there are changes as well in the sort of hormones that get released by the uterus lining. So in terms of this normal reproductive cycling, there can be negative influences through hormonal mechanisms as well. And there has been a little bit of work that suggests, if we're thinking about the male side of fertility, that post-insemination, high levels of urea can influence sperm motility, which again might be to do with the pH of the uterus in situations where we have high levels of urea. So there was a very elegant study that was done by a research group over in the US who wanted to sort of look at where this issue with urea, where it might be relevant to conception. And what they did is they took some adult cows that were around 40 to 100 days in milk. Some of those cows were fed a ration that promoted a high level of urea production, so average blood ureas were around 8.2 millimoles per litre, which is pretty mega. And some animals were fed a moderate urea ration, so it was sort of, again, elevated but not too high. They then served those cows and harvested the embryos that resulted from the conception after around 7 days. And then they took those and they transplanted them into some virgin heifers. And some of those virgin heifers were fed, if you like, a high urea ration again. So their blood urea was on average about 8.9 millimoles per litre. And then they also gave it to some other heifers that were on a very low urea ration. So their blood levels were around 2.9 millimoles per litre. And they did it with the moderate urea cows and looked at what influences this had on conception. And what they found was that pretty much all the embryos from the high urea cows, so that were harvested again 7 days after conception, pretty low chance of holding in those virgin heifers. So I think it was in the high urea animals it was around 17%, in the low ureas it was about 7%, but they're close enough to be, if you like, roughly equivalent. There was not any statistical difference between those two. However, the cows that had moderate sort of levels of urea had, again, much higher levels or much higher conception rates, regardless of whether they ended up in high urea heifers or low urea heifers. So the take home from this piece of research was that really the main influences on urea, on conception chance, tend to stem back to the period around the time of conception. So it's really early days, that first 7 days of life, where the influences are most important. And there doesn't appear to be a huge sort of carryover effect from that. So we know that urea can have an impact on fertility, but does it always cause issues in all circumstances? Well, there's been some work that indicates that cows can adapt to high urea levels over time, or high levels of rumen degradable protein being fed. So what we can take from that is that probably it's sudden increases or significant changes in urea status around the time of conception that are going to have the biggest impact. So if we think about this in terms of a spring calving herd in our country or New Zealand, most of those animals will have been out for a fairly significant amount of time on lush grass before we try to get them in calf. So this is one of the reasons that we probably don't see significant influences on, or negative influences on fertility in those sort of herds. The challenge comes for, if you like, a year-round calving herd which grazes or is going to feed some very high crude protein silage. That sudden increase, you have to be serving 365 days a year. You are probably going to see a reduced risk or reduced chance of pregnancy, I should say. So I guess the question is, right, we know urea can be too much, but how much is too much? There was a recent meta-analysis that was done, which is effectively a great sort of way of getting several studies and combining them all together to try and come up with a clear answer. And the conclusion from that was effectively that if you looked at blood urea in cows, if you have more than around 7 millimoles per litre in the blood, which equates to around 4.2 milligrams per litre in milk, that is likely to have a negative impact, at least in the short term. Bulk milk urea, of course, is an incredibly tricky thing because, of course, it takes no account for different cows' intakes, different cows' diets. And so all you can say is that if your bulk urea is very high, then you can be relatively confident that several of your animals will, probably have too much urea washing around. If it's very low, then again probably you've got very low levels of urea production, which again shouldn't be an issue, but if it's too low it can impact production. If you've got something anywhere in between, then it doesn't really tell you much at all, unfortunately. So we are reliant on individual cow sampling to really understand what's going on in our herds, rather than bulk milk urea, which is a very, very crude, blunt tool. And certainly if you go sampling, this was a group of cows as a piece of research into ketosis that I was doing. I went out and sampled around 1,000 cows. And when we looked at the blood urea levels, which was just sort of a side sort of distraction in the project, I did find that the time that 6.8 millimoles per litre was the cutoff that most people were talking about. I found, a good sort of 10–15% of those animals had high levels of blood urea. And of course that tends to cluster by herd. So this is again a herd specific issue. Many of the herds had no such issues whatsoever, and a few of them had very, very high levels or high percentages of animals with urea, and these were animals in the first 60 days of lactation. So back to farm P. So we obviously we noticed that the bulk urea levels were high. So the first step was initially sort of trying to characterize the forages. So in the UK there are 3 basic types of analysis that can be done on forage. One is the sort of the gold standard, which is sort of literally the test tubes and people in white coats approach, which is we tend to call it wet chemistry or proximate analysis. That is, it's an extremely sort of expensive way of analysing things, but it is obviously the sort of gold standard and very accurate. We then have a type of, if you like, cheap and cheerful way of analysing our silages, which tends to be based around this what we call near infrared NIR technology. What this basically does is they get a bunch of samples and they do the proper wet chemistry analysis, and then they look at how infrared light reflects off those different samples, and they try and relate the two. So that when you send a new sample in, they can look up in their database and say, look, we'll bounce some infrared light off this. It looks very similar to this pattern from an 18% crude protein silage, so therefore we'll call that 18%. So the reason we did this was just to see, one of the things that you can get caught out with is if you have very unusual silages, then it might be that the predictions for those aren't particularly accurate. So NIR is best at predicting fairly typical kind of things. It doesn't do wild and wacky. So if you undersow peas under whole crop and send that in for a crude protein using conventional wet NIR, you can get some pretty wonky results. So I think what we took from that, and we looked at these different analyses, is that the crude protein in the silage that was being fed at farm P at the time, which was third cut silage, very wet, hadn't been made in the best of situations. First of all, it had a very high crude protein level already, and when we looked at the proportion of that crude protein that was ammonia, it was very high. So in other words, a lot of the protein had been in the grass had been degraded during that silage formation, and that of course means that you've got a lot of very soluble nitrogen rushing into the rumen every time that cow has a bite to eat. I mean, the ration itself, we took a look at that and said, right, okay, we've got the grass silage, we've got a fairly good idea on what it is. How is it sitting in the ration? What's the ration doing? So the diet itself was formulated by a very well-respected nutritionist over a lot of time. He's very good. And we sort of ran it through. I ran it through an alternative model, which is a US-based system. It's a bit unusual in this country, but it does make, if you like, estimations on how much rumen ammonia is going to be produced, what the sort of milk urea might be, and actually the actual energetic cost of producing that urea. And so the ration was very well formulated, but what we did learn from in light of those new silage analyses is that, again, this grass silage was predicted to produce a lot of ammonia, and as a result there'd be an energy cost to doing that, and we expected to see high milk ureas, which of course we were seeing. So the next step on from that was really say, right, okay, well, obviously the rations ration is what it is, what's happening in the cow? Because of course our best predictions by computer modelling are only take us so far, and actually the best thing to do is actually ask the cow how you go. So we took some blood samples, and we not only looked at urea in these cows, but we also looked at other things that might be impacting fertility. So in this case we looked at BHBs, which are a type of ketones, so we're looking for subclinical ketosis there, and we sampled NEFAs, which again are a measure of how quickly cows are moving fat from their body reserves into their system for digestion or for cellular degradation and energy. And we then also looked at what was going on in terms of conception rate. Of course, this is rather retrospective, because of course we had to wait for animals to be first of all served and then of course determined pregnant. So this is for a few of you probably come across this before, this is a Q-sum plot. So effectively this looks at conception rate over time, and it's the steepness of the black line that is effectively an indication of the conception rate. The green and red lines in this, effectively the steepness of them shows what a certain conception should be like. So if you had a perfect 50% conception rate, it would sit slap bang on that blue line. If of course it was a 40% conception rate, it would follow the 40% conception rate line, which is sort of this line here. It would follow that perfectly, but of course we see ups and downs over the season. So what stood out, this is obviously back at the beginning of January, we saw still a very good conception rate. It was running around sort of 40-45 on average. We had then an exceptionally good month in May, when animals seemed to hold left, right and centre, huge conception rate of 73%, and then June, July, it was sort of levelling out. Fairly disastrous time. Not many animals served in August, but those that were served didn't seem to get in calf particularly well. So if we look at the blood results in the context of this, so our first sampling we visited in May. The first set of samples got taken right at the beginning of July. What we found is that, yes, as we suspected, bulk ureas were high, and individual cow ureas were relatively high here too. So I've highlighted what I call very high ureas, so the ones above 7. So 3 out of the 9 animals sampled had very high ureas, but all the others, at least 2 of them were, I would call, elevated, 6.4, 6.4, and actually 5. There's one cow with 5 millimoles per litre, which again is a bit elevated. Interestingly, what else we found is that there was quite a bit of subclinical ketosis. There's certainly more than I would be comfortable with. So if you're sampling sort of three of the 9 cows having high BHBs, makes me think that there is an energy implication or energy disease sort of implication there. Now that could be because of the urea putting additional energy costs, or it could be separate things going on with the transition cow system. Again, the transition cow diet was fairly straightforward and well formulated. Wasn't particularly anything that stood out about it, and the cows themselves looked in reasonable conditions. A couple of slightly heavier girls, but we all have them. And the actual transition cow system, in terms of feed space, looked reasonably good. So what we effectively did was, we had to feed this third cut grass silage. There was no way around that. So what we did, so the nutritionist reformulated and increased the proportion of starch and sugars in the ration, so that there was a more readily accessible form of energy for the bugs to try and capture more of that ammonia into microbial protein and have less urea produced. So we went back and sampled around the beginning of August, a month later, and I suppose the nutritionist had sort of fixed the issue, so ureas were back to sort of a normal range, and that's all looked very respectable. But and again, I wouldn't like to pretend that there's a perfect answer to this, but certainly the issues with subclinical ketosis hadn't gone away. So if we think about that particularly poor month of conception, it will have been possibly influenced not only by the urea, which may have well inhibited egg development and early conception, but I think it then followed into issues with subclinical ketosis and transition K problems. So without any particular changes to the transition K system, it was obviously discussed and reviewed between the farmer's vet, nutritionist, and obviously the farmer himself. No radical changes were made off the back of that, but there was a sort of will to sort of resample these and see if there was still an issue, or whether that was just some sort of blip that was going on at the time. And actually, if you got to September, a month later, you'd find that although there were some mildly elevated BHBs, these weren't by any means sort of severe. And again, fat mobilization, there was 1 animal out of 9, which you expect some. That's sort of an acceptable. We accept sort of 15% as being effectively normal. So what did we learn from this? So I think there was some fairly convincing sort of evidence that certainly either the high blood ureas or the subclinical ketosis, or probably most likely a combination of the two, did have some negative impacts on conception rates in August. The thing we also learned is, of course, that if we hadn't done any sort of metabolic monitoring or blood sampling, we probably wouldn't have identified any of these issues. We wouldn't have known what the individual cows' ureas were. We wouldn't have known there was an issue with metabolic disease in the transition and early lactation cows. So again, that is very important to have some sort of monitoring system in place, particularly for sort of reasonably high output herds. We also learned that some grass silage is difficult to feed. In this circumstance, we had a lot of say that third cut with a very high level of crude protein and a very high level of ammonia. We had to feed it. It was the only thing available. Had we had slightly different circumstances, we could of course diluted it down with other forms of grass silage, or even better, whole crop and maize, and that would have certainly probably helped the cows cope with that particular forage. But we didn't have it in the circumstances. So what we did do is try to increase the amount of starch in the ration and effectively the amount of energy that was available to bugs, and that did seem to, of course, bring that third cut silage back into something manageable, which was reflected by the normal urea results following that change. Of course, the bigger question is how we can avoid this in future, which is a little bit tricky, but effectively that third cut grass silage, because it wasn't particularly well made, had a higher proportion of ammonia in it right from the start. So I guess it comes back to making good silage and following good practice in terms of making sure you get a good harvest out from the field with minimal losses, so it's not down drying too long, it's down for 24-48 hours, in the clamp at the right dry matter, of course this is quite wet, and that there are sufficient sugars in there to ensure that there's a rapid fermentation and that protein is nicely preserved. So use of obviously silaging techniques such as ensuring good compaction and everything else, but also potentially putting insurance policies in place like silage additives, inoculants and so forth. Anyway, I'd like to thank Farming Connect for funding this piece of work, and if any of you have any questions, then please feel free to get in contact. Thank you.